next one is the angle of repose. And here, to understanding the angle of repose, you can take one body which is placed on a rough inclined plane. So this is the diagram represent a body which is placed on a rough inclined plane that is making theta angle. Initially, the inclined plane, this is the inclined plane, right? This inclined plane is making an angle theta along x direction. Okay. So in that case, already I explained you the weight of the body always acting downward direction only, and the normal reaction is always acting normal to the surface. Means surface is an inclined surface, so normal means perpendicular to the surface. Okay, this is the normal force direction. This is the weight direction. But here, when you are increasing the theta, you are increasing theta furtherly. What happens? The inclination of the surface, the inclined surface angle is increases, right? So when the inclined surface angle is increases, so at a particular angle, the body starts moving downward direction. Okay, and it starts moving, sliding downward direction. That maximum value when you are increasing, when the body slides down, that angle we represented as a angle of repose. Okay, generally the angle of repose, we are increasing that theta value. So that's why it starts. Suppose you consider the body starts sliding downward direction. You are increasing the theta up to 5. Okay, so this phi we represented or we call it as a angle of repose. Okay. Once again, I told you here the angle of repose means with the increasing in the angle of inclined surface. See here, the inclined surface angle initially theta. Okay. Now this the angle of inclined surface, if you are increasing, okay, with the increasing of angle of inclined surface at one angle, one maximum angle at a phi. Suppose let us take at a phi angle, the body starts sliding downward direction. The body starts moving downward direction. Okay, so that maximum angle, which is called it as a angle of repose. Okay, so this is about the angle of repose. Now, one more thing I will explain here. What is that here? When you are considering the body on the inclined surface, see here, this is the body, right? The weight of the body is acting downward direction. In that case, with respect to inclined surface, W, what about the W force? Is it horizontal force or vertical force or inclined force? Check here with respect to inclined surface. I am asking with respect to inclined surface, what about the force W? That is inclined force. Why? Because if you consider with respect to inclined surface, this is the inclined surface, right? So with respect to inclined surface, so this is the inclined force. Okay. Now you can resolve any inclined force into component forces. Means x component force and y component force. Now, how can you resolve this weight into component forces? Why? Because when you are applying the conditions of equilibrium, you should take only the x component values and the y component values. Okay. So any inclined force is there, you have to resolve into component forces. How can you resolve into component forces? Now, here, the theta, you can transfer this theta here. How can you transfer this theta? We already discussed about this moving of the theta from here to here. How? Because if the inclined surface making an angle theta, the perpendicular drawn on the surface also makes the same angle theta. Okay. But if the inclined surface making theta along x direction, the perpendicular drawn on the inclined surface. See here, the perpendicular, this is the theta, right? So the inclined surface is making an angle theta along x direction. Now, the perpendicular drawn on the inclined surface also makes the same angle theta along y direction. Along y direction means here, okay? So this theta, you can transfer to here. Okay. Here the inclined surface is making theta angle. Now the perpendicular drawn on this surface also makes the same angle. So like that, here theta is represented here. Okay, the theta is represented here. After representing this theta here, you can resolve into components. One is x component, one is the y component. Okay. Now the initial I told you initially the theta side always will be the adjacent side. See here, this theta side is always the adjacent side. The weight is W. Then what is the component value of this adjacent side or the adjacent force here? W cos theta. W cos theta is the value of the vertical component. And what about the horizontal component value? This value will be the opposite side. So that's why W sin theta. W sin theta is the horizontal component and then W cos theta is the vertical component. Okay, so like that, you have to resolve a weight value into two component forces. Why? Because this weight is inclined force. This weight is the inclined direction with respect to inclined surface. Okay. And see here the diagram, already I told you this diagram, if you consider, you consider the equilibrium conditions. What are the equilibrium conditions? The first equilibrium condition is sum of x components equal to 0. Means fx equal to 0. This is the first equilibrium condition. Okay. So according to the first equilibrium condition, what are the horizontal forces with respect to inclined surface? See here, the frictional force is horizontal with respect to inclined force, and W sin theta is also horizontal. Okay, so that's why here these are two equal. Why? Because the single horizontal force towards right down is there, and a single horizontal force is towards left is there. So sum of the rightward forces equal to sum of the leftward forces. So that's why when you are applying the equilibrium condition, F equal to W sin theta. F equal to W sin theta. Okay. And similarly, you are applying the second equilibrium condition, that is sigma Fi equal to 0. This is the second equilibrium condition. In that second equilibrium condition, if you consider the y components, what are the y components? N is the vertical component. See here, with respect to inclined surface. See here, always the reference line is the inclined surface. Okay, with respect to this inclined surface, N is a vertical component. And W cos theta also vertical component. See here, W cos theta is a vertical component with respect to inclined surface. This is the inclined surface. With respect to inclined surface, W cos theta is a vertical component. Now, sum of the upward force equal to sum of the downward forces. In the out of these forces, only one upward force is there, that is N. Equal to sum of the downward forces means only one downward force is there. W cos theta. W cos theta is the downward force. Okay. So like that, you will get here N equal to, means here the N equal to W cos theta and F equal to W sin theta. See, F equal to W sin theta and N equal to W cos theta. So after writing these equations, then you divide the second equation with the first equation. The second equation is the W sin theta divided by W cos theta. W cancelled and the sin theta by cos theta will give the tan theta and the F by N. Okay, F by N equal to tan theta. Okay, so the same relation you will get in the angle of repose. See here, when I am explaining here, the tan theta equal to F by N. Okay, so now here F by N means you can write down the mu equal to F by N. Okay, now this you keep it side. At the same time, the phi is the value of theta when the motion is impending, right? The frictional force will be limiting frictional. Okay, this phi that is a this phi means angle of repose, and theta here the alpha. Alpha means here when the limiting frictional force is there, the angle of friction is known as a alpha. Then tan alpha equal to what is the formula? Tan alpha equal to F by N. Now, tan here tan phi. Okay, so here up to the maximum value, it will you will get here the tan phi value equal to F by N. Okay, tan phi if you take at the angle of repose. So by taking the angle of repose angle phi means here the theta if it is increases up to the phi. Why? Because this theta same, right? This is also phi only. So that's why tan phi is equal. What is the formula you will get? Why? Because this theta, by knowing this theta, you have written this equation, right? Tan theta equal to F by N, this theta. Now, angle of repose is increased up to the phi. Phi means the maximum angle at which the body starts sliding downward direction. That is called, simply called as a angle of repose. Okay. Now, tan phi is equal, you can write the F by N. Okay. Tan phi. In the place of the theta, you can write the phi means the angle of repose. Okay. Tan phi equal to F by N. Now F by N equal to mu. So write down F by N equal to mu. At the same time, mu is equal to tan alpha. In the previous, we discussed already tan alpha is equal to mu F by N. So in the place of the mu, tan alpha, write down here. And phi equal to alpha. Okay. Here the phi tan cancelled here. And phi is equal to alpha now. What is phi and what is alpha? Phi means angle of repose. Okay. And what is alpha? Angle of limiting friction. Why? Because actually angle of friction only, but here the alpha we consider when the friction reaches maximum value. So that's why angle of friction. Otherwise, you can write angle of friction as angle of repose is equal to angle of friction. Okay. So the value of the angle of repose is the same of the value of limiting angle of friction. Otherwise, angle of friction. Okay. This is about the how you can equate the angle of repose is equal to limiting friction force means you have to derive like that. Okay, so let us take the components and equate the components by applying the equilibrium conditions. Then write down the equation F by N equal to tan theta. From that you can write down tan phi equal to F by N, and if it is equal to tan alpha, then phi equal to alpha. Okay. At last here the last period part is the cone friction. So here the cone friction means, what do you mean here? We are imagining a cone formed by revolving a resultant of the normal reaction and the limiting frictional. Here already how to get the resultant I explained earlier. The resultant means this is the resultant of two forces. What are those? Normal reaction force and the frictional force. If you resolve these two forces, okay, the two forces are replaced with a single force, that is called as a resultant. Okay, now the resultant, if you are revolving 360 degrees, means it is revolving 360 degrees like that. Okay, if you revolving this resultant about which axis? Normal reaction, about normal reaction. If you revolve this resultant about normal reaction, if you revolve this resultant about normal reaction, then the shape will be the cone shape will get. So that's why generally that name we call it as a cone friction. So here the cone friction nothing but is the imaginary cone formed. Why? Why the imaginary cone means why we have to consider, or the when we have to consider the cone friction. When we have to consider means here actually the body moving towards rightward direction means actually the frictional force direction is towards left. Okay. In the second case, I am rotating somewhat this body and applying in this direction force P. Okay. Next, I am applying the direction of the force P applying in this direction. I am applying the force P in this direction. Like that 360 degrees, I am applying the force like that. Okay. When the body is subjected to the force towards 360 degrees, for external force opposes the friction. Always the force is opposes the friction. So In all conditions, the force is opposes. Okay. And if you take that frictional force and the normal reaction force, one resultant will be there. In all resultants, if you are gather it, then you will get the shape is a cone shape. Okay. So here, this type of friction is particularly, it is used in some application here when the body is subjected to force towards 360 degrees. Okay. In that case, the cone friction is considered when the body is subjected to the force towards around 360 degrees, not only the single side. Okay, if it is force subjected the single side force, only the frictional force opposes the external force. That's all. But if this body is subjected to forces towards around 360 degrees, so then the cone is formed by taking the resultants of these all frictional forces and the normal reactions. If you form a resultant as a cone, okay, why? Because that's why here it is an imaginary cone is formed by resultant of R. Okay, so this is about the cone of friction. And the next one is important laws here. These are the Coulomb's law of dry friction. Why? Because these are laws are applicable only for dry frictions. Okay. So let us see what are the laws of dry friction. Okay. See here, the first law, you know, that is the frictional force is always acts in the direction opposite to that in which the body tends to move. Okay. This is the first law. According to the first law, the frictional force is always, it is opposite to the body which tends to move. Why? Because that is the opposite force to the external force. And till the limiting frictional value is reached, the magnitude of frictional force is exactly equal to tangential force which tends to move the body. Here, you remember that the limiting value means if it is reaches the maximum value only, up to the maximum value, how the frictional force? The frictional force is exactly equal to opposite force, means external force, means tangential force, that force which tends to move the body. Okay. This is about the second point. And coming to the third point, the magnitude of limiting friction bears a constant ratio to the normal reaction between the two contact surfaces. Here, the magnitude means the value of the limiting friction bears a constant ratio. Means here the coefficient of friction. That means here the coefficient of friction means that the limiting friction to normal reaction, the ratio. Okay, that constant ratio of the limiting friction to normal reaction, it is maintained between the two contact surfaces. Okay, so this value always same for the two contact surfaces. Okay, suppose you are taking the two materials, this is the one material and this is the one more material. Okay, now these two are contact at this point. Now in that case, the coefficient of friction mu is a constant. Suppose if it is 0.3, always it is 0.3 only. It will not vary. Why? Because these are the two contact surface. This is one material. This is the another material. Okay. Now, if the material changes, then the mu value will be changed. But the contact surface is same. So that's why here the constant value is maintained. The magnitude of the limiting force to normal reaction force between the contact surfaces. And the next point is the force of friction. This depends on the roughness of the surface, smoothness of the surfaces. Okay, here you know the friction is mainly depends on the surface roughness. See here, if it is roughness is more, the friction force is also more, and if it is smooth, the friction value will be less. And the force of friction is independent of area of contact between the two surfaces. Here, the force of friction only depends on the roughness of the surface. It will not depend on area of contact. Here, it is not depend means independent. Why? Because here the area, it will not depend on the area. How much area it is contacted, it is none of the point. Only it is mainly depends on contact surface due to the irregularity. So that's why surface roughness only the main role to increase the friction. So that's why the friction force is mainly depends on the surface roughness, not on the surface contact area. And the last point is after the body starts moving, the dynamic friction comes into play. Okay, so you know that up to the body at rest condition, the friction which is developed by the body is known as a static friction. Okay, when the body starts automatically the friction value is reduced, right? It is that is known as a dynamic friction. The dynamic friction is comes into play. The magnitude of dynamic friction, which is less than that of limiting friction. Okay, this point you remember that magnitude of dynamic friction, which is less than the limiting frictional value, limiting static limiting frictional value, right? So that's why it bears the constant ratio to the normal force. So at the same time, dynamic friction also it maintains the same ratio. So means mu. Okay, mu k is the constant value. It is maintained. So this constant value we call it as a coefficient of dynamic friction. So mu k is known as a coefficient of dynamic friction. So here this constant is the value when the body under motion condition. So when the body starts moving, then only we call it as that friction is called it as a dynamic friction. The dynamic friction value, which is always less than the static friction. The dynamic friction, we also call it as a kinetic friction. So that's why we are using the Fk is the symbol used to represent it. And the Fs is the static friction value. And the Fs max is the limiting friction. See here, this Fk is the kinetic friction or dynamic friction. Fs is a static friction. And the Fs max is the limiting friction. Okay, these are the different types of frictions like that. So these are the theory concept is completed. Now let us move to the problematic concept here. Let us take one some what are the conditions we have to take before going to solve some problems regarding to the friction. So with the initial conditions that I told you here, the body generally you can place it on a horizontal. Means here the applications if you consider generally the bodies are moving on horizontal surfaces. At the same time, some bodies are maybe in the inclined surfaces. So that's why we are considering the two surfaces. Okay, the first surfaces, let us consider the horizontal plane. Now, how the equilibrium of a body on the horizontal plane? Let us see here. Okay, now a body of weight W, which is rest on the horizontal surface. Initially, you consider as W is the weight of the body. So the weight of the body, which is rest on the horizontal surface, and mu is the coefficient of friction between the two contact surfaces. See here, the body is contact with the horizontal surface. So you can take the mu equal to coefficient of friction. The least force P is required to move the body depends on the direction. See here, the P is the least force or the minimum force which is required, okay, to move the body in its direction. Means which direction it is? Right side, means right side direction. Okay. At the same time, when the right side force is applied opposite direction, the frictional force is developed here. Okay. And R means here the normal reaction force. I told you the normal reaction force is always opposite to the weight and according to the Newton's law and perpendicular to the surface. See here, the direction is perpendicular to the surface. Okay. These are the initial conditions. After taking that initial conditions, let us consider the two cases. The first case, the external force, so P is horizontal force, okay? And you can consider the two forces, means the first case is the force is horizontal. In the second case, the force is acting at an angle theta with horizontal. See, in the first case, how the force is a horizontal force. How you can say that is it in a horizontal direction? Why? Because this horizontal direction is parallel to base. See, this is the horizontal base. So the force direction which is parallel to base means this is the horizontal force. Okay, now if the force is applied horizontally, so then initially when you are applying the equilibrium conditions here, the x component forces two only are there. What are those? Frictional force and the external force. These are only the x components. So sum of the x components zero. This is the equilibrium condition. Means right side forces, sum of the right side forces equal to sum of the left side forces. So right side force is P and the left side force is F. So F equal to P. So this is the initial condition, equilibrium condition. And coming to the next equilibrium condition, if you consider the vertical forces, what are the vertical forces? W is the vertical force and R is the vertical force, but opposite to each other. So that's why sum of the upward force equal to sum of the downward force. Upward force is R and a downward force equal to W. So W equal to R. Okay, so You can write down like that. Then right, so R is equal to W and P is equal to F and F is equal to mu R. So these are the conditions or the equations regarding to the force which is applied on the body horizontal. Okay. So you should consider this type of equilibrium conditions when you want to find out the frictional forces. Okay, and coming to the next case, the force is applied at an angle theta with the horizontal. So in that case here, you are applying the external force which is making theta angle along the horizontal. So I'll show you here, P is the external force, right? So this is the inclined force, the P which is acting inclined direction, and it is making an angle theta. It is represented P making an angle theta here, right, along the horizontal. Okay, here the body placed on the horizontal surface, but the force P only, the inclined force, it is making theta angle. So in that case, I told you so many times here, when the inclined force, when you observe that any force can be resolved into component forces, right? So you can resolve into two component forces. One is x component force and one is y component force. Okay, if you, this is the first quadrant force, right? The P is in the first quadrant area. So then you can resolve this force into two components. One is x component, one is y component. The x component will be P cos theta. Why? Because this is the adjacent side to the theta. So that's why when you want to find the adjacent side, you need to apply the cos theta formula. And this is the vertical side is opposite to the theta. So you can apply here the sin theta formula, that is P sin theta. Okay. And the vertical force is P sin theta and the horizontal force is P cos theta. So you resolve this force into two components. One is the x component and the y component. So then you will get the two components here and write down these two components here. Okay, now in the place of the P, we are writing these two components, P sin theta along vertical direction towards upward direction, and the P cos theta is towards right. Now you apply the equilibrium conditions. The first equilibrium condition, sum of x components equal to 0. What are the x components in this diagram? So F is x component and P cos theta also x component. Okay. F is x component and P cos theta. Is there any other x components are there? No, nothing are there. So that's why here F equal to means left side forces, sum of left side forces equal to sum of the right side forces. So from that you can write F equal to P cos theta. F equal to P cos theta. Now coming to the second equilibrium condition, that is sigma Fi equal to 0, vertical components. So in that, what are the vertical components are there? Resultant and weight. And one more vertical component is there, P sin theta. See here, the P sin theta is the vertical component. So resultant, it's not a resultant, normal reaction force and a P sin theta and a W. These three are the vertical forces. Now, when you are applying the equilibrium condition for the vertical forces, sum of upward forces equal to sum of the downward forces. Okay, so what are the upward forces are there? Let us see in the diagram. See here, the normal reaction force, that is R. R is the upward force. The direction arrowhead is towards upward direction. And P sin theta is also upward force. The direction of the arrow is towards upward direction. So you can write that equation, sum of the upward force means R is the upward force plus R plus R plus P sin theta. Sum of these are the upward forces. Okay. And what about the sum of downward force? Sum of upward force equal to sum of downward force. What about the downward forces? Here the downward force only W is there. If you observe that here, only W only the downward force. Other downward force not there. So it is equal to W. So R plus P sin theta. See here, R plus P sin theta is equal to W. So we are resolving the forces along vertical direction. Then the equilibrium condition will be W equal to P sin theta plus R. When you resolving the forces horizontally, then you will get the F equal to P cos theta. See, F equal to P cos theta. So these equations you will get while solving the problems like that. And F equal to mu into R, you know, that is R means a normal reaction. Don't confuse here. It's not a resultant here. This is a normal reaction force. The reaction force is represented with the symbol R. the place of n. Okay, F equal to mu into R. Okay, and R we have written in the W minus P sine theta. So from the first equation, so you can write down the normal reaction equal to this P sine theta. If you move the left side, that is W minus P sine theta based on the horizontal surfaces. Now let us see the body which is placed on the inclined surface. So in the equilibrium of your body on the rough inclined plane. Okay. In the previous case, you have considered the equilibrium of your body on horizontal plane. Now, in that case, the body which is placed on the rough inclined plane. So that's why you consider the equilibrium of your body on a rough inclined plane. So here, when you're considering a rough inclined plane, that so this is the inclined plane and it is making theta angle. Okay, this plane is making theta angle with respect to horizontal, and the body is placed on the inclined plane. Now the body will need an external force to be maintain equilibrium. Generally, the magnitude of force is depends on its direction only. Okay, so that's why here, what are the force directions we have to consider for the body which is placed on the rough inclined plane? Okay, see here the three cases. The first case, the force P is parallel to the plane. Okay, the first case is let us take the force P parallel to the plane. Means I am taking here how the force in this direction here. This is the P, force P. It is parallel to inclined plane. This is the inclined plane. How this P here, it is parallel to inclined plane. This is the first condition. Okay. In the first condition, the force is parallel to the plane. Okay. And next move to the second condition. The second condition, the force P is horizontal. So how could you take the force along horizontal? See, this is the force P. So this force is in the previous case, the force is parallel to plane. See here, the force P is parallel to plane. And in the next case, force P is horizontal, means this is the horizontal plane direction, right? So if it is parallel to horizontal, then that case is known as the force P is horizontal. Okay. And the third case, the force P is inclined at an angle theta with the plane. So in the third case, you have to take that force P is the inclined force. It is making theta angle. See here, this is the third case. The first case is parallel, and second case is horizontal, and third case is inclined.